Yes, so today we need to talk about, we need to revise this part, fundamentals of deep learning, which we did last time. So we will go through the part which we did last time, just to quickly revise what has been, what we discussed last time. Okay. So, last time we talked about what is deep learning. So in fact, deep learning, it's a sub area of machine learning, and the machine learning itself also, it's a sub area of artificial intelligence. So compared to machine learning, deep learning can be automatically extract features. The difference between maybe shallow learning and deep learning, in shallow learning, we need to work with the data, we need to extract features, we need to find, we need to make it simple for the model. So when we are working with a feature extraction and feature engineering, we try to simplify the problem to our model. But in case of deep learning, we don't need to do this because we have some convolutional layers which can automatically extract those features from the raw data. So this is what is deep. Also, last time we talked about what deep in deep learning, for example. So it's a deep. It's not about deep understanding, but it's a number of hidden layers, for example. So when the number of hidden layers is more than two, for example, more than or equal maybe 2 or something, we can consider it as a deep learning model. And as you can see here in this example, we have some input images. We apply it to layer 1, for example, the first hidden layer, and the hidden layer will process the data and it will transfer it to the second layer, and so on until we reach layer number 4. And layer number 4 here, we can consider it's a classification layer. We can call this one, it's the classification or the decision-making layer. We will do classification in this last layer. So as you can see here, this is digit number 4. And the output here will be one of the 10 classes, so it will be class number 4. This is the main task for us. So we can say that it's multi-stage representations. Each layer will have its own representation of the data set. And finally, we can make final decisions in layer number 4. So layer number 1 will have its own representations. Maybe this first image, maybe it could be for example, in iteration number 1, for example. Also, it will transfer this representation to layer number 2. Layer number 2 also will process it, and it will have also its own representation, and so on, until we can reach a decision. Maybe the decision at the beginning, it will be random, but in each iteration, so maybe this is iteration number 1, for example, this is in iteration number 2, and so on until we reach iteration number n. And then when we are in iteration number n, maybe at that stage, we will have more representative representations of my data set, and we will be able to correctly classify our data set. How learning works, we know this one very well. We have some data, right? And we will apply those data into some layers, and each layer will do some data transformations, and it will transfer those transformations to the next layer until we are reaching the output layer. And the output layer, it will do some predictions, and we will take we will subtract predictions from the true target values, for example. So it will be y minus y dash, for example, and we will calculate the loss function. So for example, this loss function, it could be 1 divided by 2 summation of maybe y minus y dash square, for example. So it's mean square error. So this is a loss function. You can select your own loss functions. So finally, we will have this one loss score. And the target now is to use an optimizer, and this optimizer will try to adjust the weights and the bias in a way that minimizes this loss function. So the role of the optimizer, it could be error band propagation, for example. It so try to select weights and bias in a way which minimizes this loss function. We have this example, MNIST data set, and we need to build a feed-forward neural network using sequential API from Keras, for example. So we need to define a model, which is an instance of sequential API, for example. We need to define our model. It could be a number of layers. So for example, the first hidden layer, it will consist of 512 neurons. And the input to this layer will be the shape of the input image. So it will be 28 times 28 pixels. So the input, you can say that it is the size of the input layer. It will be 28 times 28 because the input image is 28 times 28 pixel values. In case we are working on pixel values, you can give this layer also a name. So I can call it, for example, first hidden layer or hidden layer, for example. I need to select the activation function, which is RALU, for example. It could be followed also by dropout to avoid any overfitting. And after that, we will have the output layer. And the output layer, for example, it will consist of 10 neurons because we have 10 classes. I mean, in MNIST dataset, we have 10 classes. So number of neurons in this layer, it should be equal to the number of classes. So this is very, very simple, straightforward neural network, which consists of one hidden layer and one output layer. After that, you need to compile this model. You need to select the optimizer, for example. You need to select the loss function. So because it's a multi-class classification problem, so we will select the loss function is categorical cross entropy. This is the evaluation metric, which is accuracy, for example. So we need to maximize this accuracy, for example, and minimize the loss. At the end, I can use plot model.summary, for example, and the plot model, so I can get all those details from our model. So in fact, this model, it's very simple. So we will have one hidden layer, and it will consist of from 1, 2, until 512 neurons. And the output layer, it will be 10 neurons. So it will be 1, 2, and 10. So just make all those connections, right? So this is our feed-forward neural network. And of course, the input here, it will be because my image is 28 times 28 pixel values. So I will supply those number of values, and I will transfer those numbers, those values to the hidden layer. So the input layer, in fact, it will do nothing. It will just transfer those pixel values to the first hidden layer. And the first hidden layer, it will do some data transformation, and it will transfer its output to the next layer, which is the output layer. So as you can see here, the model consists of one hidden layer and one output layer. So the input layer, it does not have any parameters here. This is the first hidden layer, or the hidden layer. Number of inputs will be 784, and the number of outputs will be 512, as we defined it in this line, in the first dense layer. And we use the dropout. The dropout does not have any parameters, and the output layer, it will consist of 10 neurons, and number of inputs will be 512. So if you want to calculate number of parameters, for example, for the first dense layer, it will be this number. And if you want to calculate this number will be 784, which is the number of inputs, multiplied by 512 plus 512. I mean, this plus 512, it's a bias. So in this case, we have this number of weights, and this is the number of bias. Of course, the dropout layer, it does not have any parameters. The output layer, it will have this number of parameters. This number will be 512 multiplied by 10 plus 10. So it will be 512 multiplied by 10 plus 10. So now we can get the total number of parameters, which will be the summation of those two numbers. So the summation of those two numbers will be the total number of parameters, which is 407,000 parameters, for example. And this is a trainable parameter. This number will be the trainable parameter, and the non-trainable parameter will be 0. Non-trainable parameter, we will see this number when we use transfer learning. So after training our model, we can see the confusion matrix, right? And as you can see here, we try to maximize all numbers across this diagonal, because this is the number of classes. So for example, this one, it's number of classes 0, which is classified as 0, right? This is a number of class 1, which is classified as 1. And as you can see here, we can see also some other numbers here, which is misclassified. So the model is confused on those cases, for example. So for example, if we can look into this number, it means we have 3 from 8 class misclassified as 0. And it's normal because sometimes people write 8 as similar to 0, for example. So, and of course, you can calculate also precision, recall, F1 score, and so on. And as I told you some weeks before, it's when you try to report your accuracy, for example, don't report those numbers as a single number, but try to report those numbers as a range. So it should be mean accuracy plus minus standard deviation, or we can use confusion matrix, confidence interval for calculating those numbers. So if you want to calculate mean accuracy plus minus standard deviation, maybe we need to run this model, maybe n times. We need to train this models maybe n times, and we can calculate those mean plus minus standard deviation. If you don't want to do this, you can just use confidence interval for getting the range. And it's important. Also, precision and recall. Maybe precision and recall is not enough. And it's also important to calculate F1 score, because F1 score, it will combine precision and recall in one number, and it will help you if you want to compare between models, between two different models. So if I need to compare between two different models, it will be difficult to use precision and recall, and it's better to combine those two numbers into a single number, which is F1 score. If you want, sometimes people want, similar to this graph here, if you want to see those intermediate values, right? I just need to define a model where the input will be this output, and I need to just display the output, or I need to get access to the output from one of those hidden layers. For example, our model has only one hidden layer and one output layer, so I will try to display some of those intermediate values for people who are curious to see how it looks like. So in this case, I need to define a temp model. So I will use model API from Keras also, and I need to define the input. So the input to this model, it will be my original model.input. So the input to this sub-model or temporary model will be model.input, and the output, it will be the output from, it will be model.get layer, the output from the hidden layer. We have only one hidden layer, and I need to get access to this hidden layer. So in fact, I just create this temp model to try to get access to outputs, intermediate outputs from some of the hidden layers. So in this case, I need to define this model using model API from Keras, and the input to this model, it will be the original input to my original model, so it will be model.input, and the output, it will be the model.get layer, and you need to select the layer which you want to see its output. So in this case, it will be hidden layer, because I called it hidden layer last time. As you can see here, we call it hidden layer. So hidden layer dot output. So in this case, we will get access to the output of this hidden layer, and after that, I will just get those temporary temp outputs. Those temp outputs, it will be my temp model dot predict. I need to predict to get those intermediate values. So for example, I will send the first 10 images. I will send the first 10 images to my temp model to try to plot those intermediate values. So as you can see here, I have, for example, the first 10 values because we shuffled. So the first digit is 721041495 for example, and those are the intermediate values. And as you can see here, it looks like, because it's 512 pixel values, you can say, or 512 values. So it looks like some random signal, 512 values. And finally, this is the output from my model, right? This is the output of my this is the output of my original model. So it's a model.output, right? Those are our predictions. So so this is the input, right? Which is 28 times 28, right? This one, it's the intermediate output, which is 512 values. You need to try to reshape it as an image. So in this case, maybe I need to reshape it as an image using those dimensions. So it should be 32 times 16, because 32 times 16 equal to 512. And this is the predictions, correct? This one, it's my prediction. So in this case, we can get access. If you want to get access to those intermediate values, it will be nice. It might be something exciting to see for your problem. Last time we talked about data representation for neural network. We will not go into it this section again, but it will just show us if you need to use mini batch gradient, for example, you need to check maybe the size. It will be exciting also to just say something about the size of your data set, the size of each batch. Why did you select a batch size of 512 or 256, for example? Of course, some people, you can do it by trial and error. So for example, if you selected the batch size equal maybe 512 images, maybe the system will not be able to process it, for example, and you need to go down into, for example, 128 images. But it will be nice to say something about the size of your data and why do you select this specific batch size. Of course, if you are working on the cloud, I mean, you don't need to care about this, because the clouds, they have enormous size, memory size. So we will just skip this one because we talked about this last time, and also those are the models which has been used. So I want to talk more deeply today about the CNN. We started the part last time. So CNN or ConvNet, the goal of CNN is to learn higher order features in the data using convolutions. I mean, if you are working, I mean, the last example was MNIST dataset. we build the system. We have been working with pixel values, so we didn't use any feature extraction techniques. But usually, when you are working with a large image, because the image is 28 times 28, which is okay. But if you try to go to an image which is 512 times 512, your model will be really very large, and your model will. I'm sure that your model will overfit your data. So it will be really very difficult to work with image size of 512 times 512 without using some feature extraction technique. But usually, we can say that in shallow learning, we try to use feature extractions. We can use principal component analysis. We try to use, for example, selecting the most important features. So we need to do some feature extractions or feature engineering to select the most powerful features to fit into our model. But in case of CNN, we don't need to do this because we can work with raw data, and the model itself will be able to extract those features automatically. So we can say that in convolutional neural network, we automate the feature extraction process. So the goal of CNN is to learn higher order features in the data using convolutions. Convolutional layer is responsible for systematic applications of one or more filters to an input. We try to apply those filters or kernels to our data, so we can extract those features. And the architecture of CNN, it consists of input layer, which accepts the image and it just transfer it to the next layer, for example. And we have some feature extraction layers, and those feature extraction layers, it's a repeated sequence of convolutions and pooling layers. It's a sequence of convolutions and pooling layers, and at the end we have some classification layer or layers, right? We have some classification layers. So you can say that it consists of an input layer, and the input layer, it do nothing. In fact, it's just to transfer my raw data to the first conv layer, for example. And in the feature extraction part, it consists of a sequence of repeated convolutions and the pooling layers. And at the end, we have some classification part or classification layer or layers, which is fully connected layers. It's like dense layers. We use the dense layer, so it will be also some dense layers which will do the decision making for us. So as you can see here in this graph, we have an input image, which is raw data, and after that we will apply some feature convolutional layers followed by pooling layers. So it could be conv layer followed by a pooling layer. So we will have this block like standard. So we'll have one conv layer 1 followed by pooling layer, and again conv layer 2, for example, followed by a pooling layer, and so on. So we will have the part which is the feature extraction part, and at the end we will have some fully connected layers which will do the decision making for us, or the classification part. So we will do here some classification, right? And it's dense layers, correct? A number of neurons in the output layer, it will be a number of classes, as you can see here, correct? And the blocks also, or the feature extraction part, it will try to extract higher order features from my raw data, for example. So it's just quickly about, I mean, this is the model, for example. So this is the model. So I have some input image here. I will, and after that, we will apply some conv layers, followed by some pooling layers, right? It's a sequence of conv followed by pooling layers, and so on. And so this one will be the feature extraction part. This one will be feature extraction part, which is the most important part, in fact, because it extracts those features. And at the end, we will have the classification part. This is the classification. And as you can see, the classification part, it consists of number of field connected layers. So it could be 1 layer, 2 layers, 3 layers, anyway. But the most important here is the output layer, which we call it soft max layer. The output layer here, we call it soft max layer, because this is the one which will make decisions. Usually we use soft max activation function here, because we need to calculate the probability that this image, for example, belongs to some class. So we calculate here, if we have 3, for example, it's multi-class classification. So in this case, we will calculate the probabilities, and the summation of the outputs here, it will add 1. So the summation of the output here, yi, for example, it should equal 1, right? Maybe someone will be 0.6, another one, it will be, for example, 0.3, and the third one will be 0.1, which means the probability that this image belongs to class 1, it's 60%. the probability that this image belongs to class number 2, for example, it's 30%. The probability that this image belongs to class number 3, for example, it's 10%. So the summation of those probabilities should add to 1. Transfer learning, what is transfer learning? Transfer learning, in fact, because this feature extraction part, this is the most time-consuming part or most computationally demanding part. Usually, we prefer to transfer this feature extraction part from one application to another application. So, for example, if I use this model for classifying MNIST, I can just train this model for MNIST, and I can transfer this feature extraction part to another application. For example, it could be MNIST fashion, for example. So I can just transfer the feature extraction part to another problem, as long as it is within the same domain. So if this feature extraction part has been working with RGB images, for example, correct? So in this case, maybe I can just transfer it to another problem where we are using also RGB images, correct? So because this is a time-consuming part, so I just transfer it from one problem to another problem. But in the other problem, I need to replace this one with my problem, because this one has been designed for example, classifying this image into 3 classes. Maybe in my other application, I need to classify into 10 classes. So I need to change the classification part. So we need to keep this part and change that part to suit my new problem or new application. And in this case, when we try to see the trainable parameters and the non-trainable, the weights and the bias of that part will be non-trainable because it's frozen. We need to frozen those, otherwise we will destroy it and we will retrain the model. So in this case, I need to transfer that part from one problem to another problem. I need to design my new classifier. This one will be new classifier. And if it is new classifier, it means the weights here are just initialized with random values. So it will do random classification at the beginning. So in this case, I need to retrain the whole model. But if you need to retrain the whole model to adjust the weights and the bias of the classifier, we need to freeze those bias and weights of the feature extraction part to avoid destroying it, because I need to keep it. I don't need to touch it because it's time consuming to retrain that part. So I need to freeze weights and bias of the feature extraction part. And in this case, we will see that we have non-trainable and the non-trainable parameters. The trainable, it will be that part. Non-trainable, it will be the weights and the bias of the feature extraction part. So for example, if you can go to, we will see some examples anyway. So anyway, the weights and the bias of that part, it should be non-trainable. And weights and the bias of the decision making or the classification parts, the fully connected layers, it will be trainable, right? Because I need to train those weights and the bias, but I don't want to train the weights and the bias of the feature extraction part. So the building blocks again, we agreed that it will consist of those convenates. It will consist of convolutional layers and maybe 1 or 2, and each one and 2 followed by pooling layer. And at the end, we will have number of those. We will have a sequence of conv layers followed by pooling layers, right? Number of those. And at the end, we will have some fully connected layers or classification layers, for example. And each convolutional layer, it consists of some filters and some feature maps. In fact, it consists of filters, and the feature maps, it will be the output. By applying those filters to the input image, we will generate those feature maps. But if you need how many feature maps, how many filters, it's something which you need to decide. So the number of filters or kernels which we need to apply, it will as the size of the filter, it's a hyperparameter which you need to decide, and also the number of filters will generate an equal number of feature maps. Filters are essential. Are essentially one neuron. Last time we agreed that each filter, for example, if it's 3 times 3, like this one. So in this case, it will be it will consist. We will have some value here, which will be the weight value. So for example, it will be omega-1, omega-2, omega-3 until omega-9. So each filter, in fact, it is composed of one neuron. So it will be like this one. It will be one neuron, and we will have those weights, right? So it will be omega-1, omega-2 until omega-9, for example, and we have here bias. So each filter will be like this one. So when you define, for example, 10 filters, so we will have 10 neurons in this layer, for example, And the size of this filter, it could be 2D and 3D. So it's according to number of channels of the input image. So if the input image is one channel, it's a grayscale image. So this one, it will consist of 9 values. If your input image is RGB image, for example, which means we have 3 channels. So in this case, this one will consist of, it will be in 3-dimensional. So it will be width, height, and the depth. So it will be like this one, correct? So it will be 3 filters, or it will be in 3D, for example. And in this case, number of weights will increase from 9 to 27. So instead of stopping at 9 here, we need to continue until we have here omega 27, because 27 is 3 times 9. And it could be more also, because some conv layers, also the input to some of those conv layers will be a feature map. Maybe this feature map has a size of maybe 128. In this case, the depth will be 128. So in this case, this one, as a filter size here, it will be 3 times 3 times, for example, 96 or 128, for example. So the depth will be the size of the previous feature map. So they have both weighted inputs, and generate an output like an input. So if you need to apply this filter to the input image, for example, we will apply it to the image. We will multiply those weight values with the pixel values, and we will take the weighted input, the summation, for example, and we will apply this summation to an activation function to calculate the output here. And this output will be the new pixel value of the new feature map, for example, respective pixel value of the new feature map, and so on. So the input size is fixed square called the batch or receptive field. This one has a size. When it's 3 times 3, we can say that the receptive field is 3 times 3. And if the convolutional layer is an input layer, then the input batch will be pixel values. When you apply this one to the input image, it will be receptive field will be pixel values. But also when you apply it to feature maps, it will be the same. I mean, I cannot see any difference. So if the depths, if they deep in the network architecture, then the convolutional layer will take input from feature map from the previous layer. So as I told you, if the first conv layer, I mean this CNN layer, for example, first conv layer, it will apply this feature maps, those filters to the input image. But if it is the second CNN layer, we will apply this filter to the feature map, which is generated from the previous layer, and so on. So the feature map is the output of one filter. I mean, those feature maps, they are the output of one filter applied to the previous layer. A given filter is drawn across the entire previous layer, moved 1 pixel at a time, and each position results in an activation of the neuron, and the output to be collected in the new feature map, or the generated feature map. If the receptive field is moved 1 pixel from activation to activation, then the field will overlap with the previous activations by field width -1. If you are moving by 1 pixel value, so there will be some overlap, which is equal to the filter width -1, or receptive field -1. The distance that the filter is moved across the input from the previous layer, each activation is called stride. So we move by one pixel value or 2, for example. We call this step side as a stride, and this stride, it's also a variable which we need to decide, right? So there is something called the zero padding, which is used to invent this mock inputs with zero values for the receptive field. It's something which we add across the whole image, for example, to avoid to be able across the edge or the perimeter of the image, to be able that to be sure that those values across the perimeter have the same importance, also similar to the internal pixel values. This is an example. We have some input, and we need to apply this kernel to this input. So we'll apply this one to this image, for example. And you can just see here, this is the original input, right? This is the original image, which is 3 times 3, and we added here zero padding, right, around the perimeter. And we will apply this kernel to that part first, which is zeros, multiply those input, those weight values with those zeros, and take the summation, weighted sum. So it will be 0 multiplied by 0, plus 1 multiplied by 0, 2 multiplied by 0, 3 multiplied by 0, so the total will be 0. And the summation, we will apply it to the activation function. It could be RALU, and we will calculate this value. So, and after that, we will move it by one by stride. If the stride equal 1, so the next move, it will be here, right? And we will do this calculation one more time. So in this case, it will be 3, right? It's not the output, in fact, this is the weighted sum. This one, it's not the output, but it is a weighted sum. We need to apply this weighted sum to my activation function in order to get this number, but we'll just make it simple here. And that's the next stride also, we will move it again by one step. So in this case, it will be 2 multiplied by 1 plus 3 multiplied by 2, which is 2 plus 6, it will be 8. Move it again, one stride, one step. And when we finish the first row, we will go to the second row. We will go down by one pixel value. We just go down. I'm starting from the same location here. So in this case, it will be 3 times 3, it will be 9. Move it by one step and so on. So the zero padding, when we apply convolutional layers, we lose some pixel around the perimeter of. If we didn't use zero padding, we will lose some information here. Or just we will scan it only one time, which is not enough, which gives the model an impression that the information provided at the pixel values around the perimeter is not very important. To avoid this, we need to add zero padding. So the pixel value describes how bright the pixel, I mean, those pixel value is just color. You can just transfer it into colors, for example. So in case of grayscale image, close to 0 means darker and vice versa. When it's 1, it's white. When it's 0, it's dark. So when it's 0, it's darker, and then when it's 1, it's a bright, right? Or stride, the filter slides 1 pixel at a time. This is by default, in fact. So if you didn't define the stride in your code, the default value will be 1 each time. So you will go from left to right by 1, and from top to down by 1, right? Top to down, and left to right. So this is how we will move. We will repeat this process several times until we scan the whole image, until we calculate also this feature map. So this one, it could be input image, and the output here, we call it a feature map, right? So number of feature maps will be equal to the number of kernels, right? Usually we don't use those. Usually we use those conv layers, and we follow each conv layer by pooling layer. This is very important. So the pooling layer, it's try to downsample the previous layer feature map. Try to downsample it, and it's very beneficial, in fact, because it will help us also to reduce number of parameters in the fully connected layers, to avoid potential overfitting. So pooling layers follows a sequence of 1 or more conv layers. So after each conv layer, we need to have a pooling layer, or after each 2, for example, conv layers, we can have a pooling layer. Pooling layers follow a sequence of 1 or more conv layers and are intended to consolidate the features learned and expressed in the previous layers. They try to consolidate, right? And do downsampling and consolidate those features which has been learned by previous layers. So they can compress or generate generalized feature representations and try to reduce the overfitting of the training data by the model. They have also receptive field, which is much smaller than the conv layer. Also, the stride or number of inputs that the receptive field is modeled for each activation is often equal to the size of the receptive field. So this one, if this one is 2 by 2, you don't need to define the stride, because each time it will move by 2 by the same size of. So usually this one, it's a square, and the stride equal to the size of this square. So if it's 2 times 2, so stride equal to. If it's 3 times 3, stride equal 3, because we cannot have any over. We'll try just to try to do some, downsampling. So for example, this one, it's a 3 times 3. Of course, this is not a good example because we have some overlap here, right? So pooling layers are often very simple, taking the average or the maximum of the input value in order to create its own feature maps. So usually it's average or max. So it's average pooling or max pooling. So those pooling layers, we have average and max pooling. When it's max, for example, it will just take it will look into this receptive field, and it will take the max. So the max here will be 4, right? If it's average, so in this case, we need to take summation and divide it by 4. So it will be 0 plus 1 plus 3 plus 4. So it will be 8 divided by 4. It will be 2. So it could be average and it could be max. Average pooling or max pooling. So at the end, just to revise, we have this input volume. This is the raw data, correct? We have some conv layers, and each conv layers is followed by 1 or 2, for example, followed by max pooling, for example, or average pooling. And at the end, we need to have this fully connected layers. The fully connected layers, it's the one which will make classification, right? So this part is very similar to feed-forward neural network, exactly the same. So we need to have number of hidden layers and one output layer. Number of neurons in the output layer, it will be number of classes. If you have 5 classes, so number of neurons here will be 5. And the activation function in the output layer, it should be softmax. And therefore they call it softmax layer. So the output layer, they call it softmax layer, for example, because the activation function here, it's softmax, and it is used softmax because we need to calculate the probability that each image, the probability at which each image belongs to each class. So summation of the outputs here should be equal 1. Before using, so this is the output layer. You need also to have some number of hidden layers, for example, of fully connected layers with maybe ReLU activation function, right? Rectified linear unit activation functions. You have connections, you have weights, very similar to feed-forward neural network. So if I want to calculate number of weights in this layer, so it will be number of outputs multiplied by number of inputs plus number of outputs, the bias. Fully connected layer, it will be the same. But there's a difference here that you can use maybe 1 fully connected layer or 2 fully connected layers as hidden layers, for example. Maybe the activation function here, it's something also you need to select, but usually people use ReLU because ReLU has good response to vanishing gradient. Before using, I mean the connection, in fact, between this max pooling layer and the fully connected layers, one layer which does not have any parameters, it's called the flattened layer. We need to use, I mean, between this conv layer or max pooling, for example, or average pooling and the fully connected layers, we need to use a flattened layer. And this flattened layer does not have any parameters. It will just convert those feature maps into one vector in one-dimensional space. So it will be just like this one column, for example, or one vector. So it will convert those feature maps. It will combine those feature maps because I don't know. For example, here we have 3 feature maps, and each feature map has a size of 14 times 14. So in this case, we need to flatten it into one vector. The size of this vector will be, for example, 588, which will be 3 times 14 times 14. So it's just combining those output volume or the feature maps into 1D vector, and that is all. And after that, we will feed those outputs into the next fully connected layer. First, a fully connected layer, or you can say that it's the first hidden layer, for example. So fully connected layers, fully connected layers are normal, flat, feed-forward neural network, as in shallow learning, no difference. These layers may have non-linear activation functions or softmax activation functions in order to output probabilities of class predictions. Fully connected layers are used at the end of the network after feature extractions and consolidations has been performed. So those conv layers will do feature extractions, and max pooling, it will do feature consolidations and downsampling. So they are used to create the final nonlinear combinations of features and making predictions by the network. This is the most important part here. You can see this is the brain of my model. So the classification part, this is the brain of my model, and that part, it's a data processing or feature extraction parts. We will use Keras for building our models. You can use also, Torch, for example. Keras provides an implementations of conv layers called the conv2D, for example, and it requires the expected shape of the input. We just need to define the input shape of the input image. Just need to define this, the input shape of the input image, which in terms of height, width, and depth. So we need to define this. We need to define this one. So the filter contains, and in each layer, we need to define filters, and the filter contains the weights that must be learned during the training of the layer, and the filter weights represent structures or features that the filter will detect, and the strength of the activation indicates the degree to which the feature was detected. The layer also requires that both numbers of filters be specified. We need to define number of not only the size, but also the size and number of filters. So we need to define the shape of the filter and also the number of filters, right? It's a hyperparameter which we need to define. So because the number of filters I mean, number of output feature maps, it will be equal to number of filters. And the size of the filter is important because it will impact the receptive field. So, and the receptive field, for example, if your image has, if this filter has a small receptive field, in this case, or large, what will be the difference? Maybe when it's large, we will scan the image faster with less number of activations. But when it's small, in this case, we need more time, in fact, because number of activations and the number of calculations will increase. So if you want to implement this deep learning in Keras, for example, you need to import sequential API from Keras.models, sequential and the model. Model is required if you want to plot some intermediate values. And if, from Keras.layers, you need to import dense layer. Dense layer, it will represent the classification part, conv layers, and the max pooling or average pooling layer. I mean, that is all. How can we build our model? So we need to define the model as a sequential API, so it will be model equals sequential. You need to add some layers. So it could be dense layer, and it could be also conv 2D layer, for example, right? As we did before in the MNIST example, but you can also add conv layer and the max pooling layers and the flatten layer. We have all those different types of layers. After building your model, you need to compile your model, and to compile your model, you need to define your loss function. You need to select an optimizer. You need also to select some evaluation metric, as we did before. And at the end, we will try to train the model using my training data set. So before doing this, we need to divide my data into training part and the testing part. We will use the training part for training our model. We need to define number of epochs, for example, and the batch size. And as I told you, the batch size will be based on the GPU memory, for example, in your computer, and the size of your data set. So this number can go up and down based on the size of the data set which you are working with. After that, maybe we need to just evaluate the model and try to get loss and accuracy, for example. Maybe plot training and those evaluation metrics, for example, accuracy and error, for example, for the training and test set. So we will do some evaluations to evaluate my model, and after that I will deploy my model where we will try to do some predictions, maybe using the test set or any new data sets. We talked last time about convolutions or filters, what is the meaning or what is the physical meaning of those filters. And we'll talk last time about edge detection filter, which you can find in any image processing book, for example. So you have those filters, you apply those filters to any image. For example, I can apply vertical edge filter to this image, and in this case, you will predict those vertical edges. You will get those. I mean, when you apply this one to that image, maybe you will get those vertical edges, for example. So you will get something like this one for, yeah, this one, right? When you apply horizontal, you will get those horizontal lines, which is like maybe this. So we apply those filters to the input image to try to get some vertical edges or horizontal edges. And before, usually people try to sum those pixel values, those vertical edges, the pixel values of those vertical edges, so can convert this one into a number and use this one as a feature, for example. And also you can calculate those pixels, and you can use this number as a feature, as an input to my shallow learning model. Today, we don't need to do this. So this is vertical edge, for example. This is, if you can find it from any, you apply this one to the image. I mean, this image, when it's 0, it's black. When it's non-zero, it's white, for example. So you can see here from this image, this is the pixel values of that part. You can see that we have an edge here, and we'll try to detect this edge, for example, by applying this filter. So I will apply this filter in that part. So the output will be 0, right? Because it's 1, 1, 1, 0, 0, minus 1, minus 1, minus 1. You take weighted sum, so it will be 1s multiplied by 10s, 0s multiplied by 10s, minus 1 multiplied by 10s, and it takes summation. So it will be 0, 0, it will be white. It will be black pixel. So it will be that part, right? You will move it by 1 pixel, and I will move here. I will apply that part to this section here. So in this case, it will be 30, just 30, which is still 30, which is white. So now I can get this white pixel. move it another pixel. So in this case, it will be also, it will be 30, correct? So which is white pixel. We will move it here to this white part, and in this white, this black part, and in this black part, we don't have any edges. So should expect that we will get a 0, and a 0, it's a black, right? So in this case, I will be able to predict this vertical edge. And at the same time, we can apply, not just rotate that one, rotate it to try to predict those vertical edges. So this is how we can do it. It's just to, understand the physical meaning of those filters. So at the end, we will have, as the most important here is those numbers. Those numbers are very important because they will define the function of this filter. We can get those numbers from any book, any image processing book. In case of deep learning or ConvNet, we would replace this one with the same filter size. So it could be the same filter size, but instead of using those numbers, we can just use some weight values. So it will be omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, 7, 8, and 9. And we will initialize, in the first iteration, we will initialize those weights with random values, right? So at the beginning, it will just try to predict some random feature map, for example. It will be just something random, but the optimizer will try to adjust those weights in a way in which we can get something which has a meaning. So at the end, we will try to get a feature map which makes sense for my problem, right? So when we train the model for 10 epoch or 20 epoch, for example, this one, it will evolve from those random initial values to some randoms, to some different numbers, which can make sense for us. It would be nice if you can train a model and you can try to print those filters and also the feature map to see how the feature map looks like, what it looks like. So other filters, as I told you, this is a vertical edge. This one for vertical edge, just to rotate it to get it for horizontal. This is also another horizontal change filter, for example. This is vertical change. So if you can open any image processing book, you can try to find lots of filters and you can understand its meaning. We'll talk about padding already. So padding, it's very important because if we need to keep the same feature map, if the output feature map, if we need to keep the same size as the input feature map, we need to use zero padding. And there are two options here. It's the same and void, right? When it's void, it means we don't use any padding. When it's the same, it means we need to use zero padding in a way such that the output feature map will have the same size as the input image. Stride, we understand now stride. So suppose we choose a stride equal to. So while convolting through the image, we will take 2 steps, both in the horizontal and the vertical directions separately. So we will go in horizontal, and after, when we finish this first horizontal row, we will go down by the same stride, and we will repeat this process until we complete scanning the whole image. This is a stride convolution of size 2, for example. We need to do this one. Imagine that this is my filter, which is has a size of f times f. We will apply it to this image with n times n, for example. So just apply it to that part, we will get this number here, right? We will move it by 2 because stride equal to. So we will move it by 2, as you can see here, by 2 steps or 2 pixels. We will move from left to right by 2 in the horizontal. We will do the convolution. So we have this overlap. We have only here a overlap in 1 pixel. We will do the calculations. We will get this number. We will get this number. Move again by 2, and do this convolutions, weighted sum. We will get this number. Now we will go vertical by 2, so we will go down by 2 steps, correct? And we will repeat this process. We will get this number. Move by 2, as you can see here. We will get this number again by 2. We will get this number, go down by 2, right? We will do this calculations. We will get this number again, until we finish this convolution, for example. So as you can see here, the size of this image is 1, 2, 3, 4, 5, 6, 7. It's 7 times 7. But the size of the output feature map, it will be 3 times 3. And so the size will shrink because we didn't use zero padding. The size of the output feature map will shrink all time if we didn't use zero padding. How many calculations? So the receptive field here is 3 times 3, which is 9 pixels. And how many activations? We did 3 activations in each row, which means we have 9 calculations or nine activations. As I told you, if you want to increase this one to, for example, it could be, for example, 5 times 5. In this case, number of activations will be less. So if you want to speed the process, try to increase the size of the filter. If you do it 2 by 2, for example, we will do more activations. Number of activations is, based on the size of your kernel or your feature map. You can see here, the filter map, it's 2 times 2, it's 3 times 3. It's 2-dimensional, right? It's 2-dimensional because the input image is 2-dimensional. If this one is RGB image, which means we will have 3 channels. So in this case, we will have also 3 channels of my filter, right? So the depth of this filter will be based on the depth of the input image or the input feature map. So we have some formulas here which will calculate the size of the output feature map. You can use those formulas. For example, so what will happen here? We have reduced the image size, not only reduced the image size also, but as you can see here, do you see those lines? So when it's heavy color, it means when it's darker, for example, it means we did some overlaps here. But you can see here the pixel values at the perimeter, those pixel values. Especially this one, it's scanned only one time. This one has been scanned only one time. This one has been scanned only one time. Maybe those are scanned maybe 2 times, right? We go here, we go down by 2. In fact, this one also scanned only one time. This one has been scanned only one time. So in this case, when we scan a pixel value only one time, it will give the model an impression that the information coming from those sides are not very important, right? So the information coming from those sides are not very important for us, right? In this case, areas which has more overlapping, it will give, it's more important to the decision making or classification problem if we didn't use zero padding. So it's very important to use zero padding so we can scan those pixel values around the perimeter the same number of times of other pixel values. So we can give those pixel values around the perimeter equal importance. This is 2D, this one 2D, so we don't have any depth. But if you have a volume, for example, so if you have an RGB image, which means we have 3 channels, so in this case also our filter should be 3 channels. But in fact, we just define the 2-dimensional, we just define width and height and width, but number of depth will be based on the number of depths of the input volume. So if the input volume is RGB, which means it's a 3D, so this one also will be 3D. But you don't need to define this, we just need to define the 2D one, right? When you apply this one to this one, so in this case, in fact, we will apply it to, it's 3 times 3. So we will apply that part, as you can see. We will apply it here also. Maybe I need to select a different color, right? So maybe it's okay. So we will apply the filter to that part. The first channel, it will be applied to that part. The second channel will be applied to that part, right? The third channel will be applied to the blue one here, correct? One time. So we will do this activation only one time for the 3 channels. We will do multiplications, so weights multiplied by weights in each channel, and we will calculate the weighted sum one time. So at the end, we will calculate a single value. As you can see here, it will be a single value. So when we apply this filter to this RGB image, which has 3 channels, we will, the output feature map, it will be 2D, as you can see here. The output feature map, it will be 2D. So if I want to plot the neuron, which is representing this feature map, it will be like this one neuron, and instead of having 9 weights, it will be from 1, 2 until 27, right? We have here pipes. So number of parameters here of this neuron, it will be 3 times 3 times 3. So it will be 3 times 3 times number of channels of the input image, 3 plus 1. So it will be 28 parameters of this filter or this neuron. So okay, so the size of the output, it will be 4 times 4 because the size will shrink because we didn't use zero padding. So the size here will shrink because we didn't use zero padding. And so the size here is 6 times 6, right? What if you want to use multiple filters? So if you will use a single filter, you will get a single feature map, correct? If you will use 2 filters, you will get 2 feature maps. So number of feature maps will be equal to the number of filters. And you need to define the number of filters in your code, right? So when you use this conv layer, for example, you need to define number of filters and the size of the filter, the dimension of the filter. So this one will be the dimension of the filter. It will be in 2D. You don't need to care about the third dimension, because sometimes the third dimension will be 3 if the input is 3. The depth of the input image will be 3. But also, it could be also very large number if this one is a feature map and has a depth of, for example, 96. So this one will be 3 times 3 times 96. So the most important here is that number of feature maps will be equal to the number of filters. This is the most important. So when you define multiple filters, in this case, you will get multiple feature maps. I guess we don't need to talk about this because it's just how we, this is the equation of each filter, for example. So we will calculate omega multiplied by pixel values A multiplied by bias. This one should be summation, right? So it will be like omega multiplied by pixel values plus bias. So it will be like this. If you want to calculate number of activations, maybe you need to find a way to do this, how many activations we need to do to scan the whole image using the stride, which we need to define as well. Okay, this is the size of the output. This formula can be used. So if the input size is n times number of a channel, padding equal b, for example, stride equal s, the filter size called f times f, the third dimension will be the same as the input image, right? So this is the output size. So it will be n plus 2b minus f divided by s plus 1. Of course, it's squared, so it will be multiplied by the same dimension multiplied by nc. Okay, because no, sorry, this is wrong. This is number of filters. This one wrong, right? This one number of filters. You can call it nf or something, not nc. This one should be number of filters. The Boolean layer, we did that already, but just for more explanations, it will do downsampling, right? And it will consolidate those feature maps, right? So when you apply this Boolean layer, for example, I guess it's max Boolean. Well, if it's this Boolean layer, if it's a 2 times 2, so we will apply it here. We will take max, so the max will be 9, right? So the max will be 9. We will move it by stride. The stride usually, when it's in the Boolean layer, the stride equals the size of the filter Boolean layer. So we will move by 2. When you move by 2, we will come here. We will take the max. It will be 2. We will go down, right? Starting from the left again. We will do here the max. The max will be 6. Move again by stride equal 2, because the size here is 2 times 2. We will take the max. It will be 3. So in this case, we will try to do this downsampling and consolidating those feature maps. We need to have an example here, and we need to implement an example. So it's AlexNet, which is a very famous model. We use it in many different applications. This model consists of 60 million parameters, and it uses ReLU as an activation function. This is the input. So the input is RGB image. This one it's RGB image, which has a size of 227 times 227 pixel values multiplied by 3, because we have RGB. So this AlexNet, it consists of conv layer followed by max Boolean, right? So the first conv layer has filter size of 11 times 11, right? So the filter size here is 11 times 11, and stride equal 4. So it's hyperparameters which you need to decide. When you apply this one to this image, we didn't use zero padding, so we should expect that the size will shrink, and it will shrink into 55 times 55. And it's multiplied by 96, which means we selected number of filters here equal 96. So we selected 96 filters. When we apply 96 filters of this size to this image, we will get 96 feature maps. But remember, this one, it's 11 times 11. It should be multiplied by the depth of this input, which is 3. So the size here, it will be 11 times 11 times 3. We will apply this one to each input. And when we apply it to each input, we have 96 of this. So when we apply this one to this image, we will get one feature map. When we repeat this process 96 times, we will get 96 different feature maps. So when we apply the first one to the input image, we will get this feature map, which is two-dimensional, and it has a size of 55 times 55. We will go to the next filter. When we apply the next filter, we will get another one like this one. So it will be the second one, the third one, and so on until we get 96 feature maps. And each filter, of course, it will be initialized with different random values because we just initialize with different random values. So we should expect that those feature maps will be different. And the optimizer, it will try to evolve those feature maps in those filters in a way to get something which makes sense. After that, we will apply max pooling. So after getting those feature maps, we will apply max pooling, which has a size of 3 times 3 and stride equal to. So it will reduce the size of those feature maps into 27 times 27. And of course, the depth will be the same, right? So we will apply this. Max pooling does not have any parameters. This one has parameters, but max pooling does not have any parameters. When we apply max pooling to those input volume or the feature map volume, it will stay the same depth, but the width and height will change. It will shrink. It will shrink into 27 times 27. So in this case, we'll try to consolidate those learned feature maps. Apply. So this is the output volume from the max pooling. We will apply this one to a conv layer, and this conv layer will have filters of size 5 times 5. And how many filters we need to get? It will be 256, correct? And in here, in fact, we use the padding. We have same, which means we use the zero padding. So we should expect when we use same, that the output feature map will have the same size as the input feature map. So it will be 27 times 27. But what will be the difference? The difference is the depth of feature maps. We will get 256 feature maps. When this one is 5 times size, we just need to define the two-dimensional, the 2 dimensions of the filter map, which is 5 times 5. But in fact, the depth of this feature maps, it will be 96 because we will apply this one to this volume, correct? So the size of the filter, it should be 5 times 5 times 96. We will apply this one. And how many of those filters? 256. We will apply the first one to the input volume. We will generate only one feature map, which has a size of 27 times 27. And we will repeat this process 256 times. And each time we will generate a new feature map until we have 256 feature maps. After that, we will apply max pooling with the same as the previous layer. It will be 3 times 3 with a stride equal to. So the size will shrink to 13 times 13 times 256. After that, we will apply another filters, which has a size 3 times 3 with zero padding. When we apply zero padding, we should expect that the feature map will have the same size. So this one 13 times 13, it will be, the first dimension will be the same. But the second dimension, the third dimension, will be based on the number of features which we defined here. So it will be 384 because we defined 384 feature filters.
Excuse me?
Yes, any questions, please?
Yes, I have a question.
Yes.
Well, I have several questions. The first I want to ask, how did you, at the first time, got 96? I saw that there was dimension 11 by 11 by 3, but how did you get 96 out of it?
Yes. When we write, I don't know if I have the code here. Okay. I will show you it in the code. So, for example, do you see here in this? Do you see the screen here now? It's convnet.
Yeah.
It's just any model, right? And here we are working with the CFAR10. It's a data set called the CFAR10. So we need to define. Do you see this number? We need to define the size of the filter. So the size of the filter will be 3 times 3. Correct?
Right.
Can you see the? Okay. And do you see the first number here, which is 32?
Yes.
This 32, it's the number of filters. So we need to define 32 filters. Each has a size of 3 times 3. So what will be the third dimension of this filter? What will be the depth of this filter? Because we are working with CFAR10, and the CFAR10, it's RGB image. This one, it's 3. RGB image. So what will be the third dimension of this filter?
3.
3. Yes, this is correct. You see the input shape? Okay. So the input shape here, we have 3. We don't need to define it because it will get it automatically from this one. When we define the input shape of the input image, so the input image will have a size of 32 times 32 times 3. So we just need to define the two-dimensional filter, the width and height. So we just need to define that this one, it's a 3 times 3. And when we apply this one to this image, which has a depth equal 3, so we will generate, do you see?
6, yeah.
One more step. I have padding equal same, which is nice here. We use the padding equal same. So when we apply this filter to this image, which is RGB image, we will generate one feature map. The size of this filter map, because we use the same here, padding equal same, it will be the same size as the input. So it will be 32 times 32, right? We agree on this?
Yes.
So the filter here, the size of the filter here, it will be 3 times 3 times 3. Why it's times 3? Because the input image has a depth equal 3. So this one must be 3. It will automatically be 3. We just need to define the first 2 dimensions, width and height. We don't need to define the depth, because the depth automatically we will get it from the input shape here. So each filter will be 3 times 3 times 3. But how many filters from those? Or first, when we apply this filter to this image, we will get one feature map, which has dimension of 32 times 32. How many filters from those? 32. So in this case, we will apply this one 32 times. So the first time we will get this one. The second time we will get another one. Third time we will get a third one, and so on until we have feature map number 32. So in this case, the feature map will be this volume. So it will be 32 times 32 times 32, correct? So as you can see here, do you see? This is the output from the conv. This is the output from output shape of this conv layer. So it will be 32 times 32 times 32. Right? I mean, the first dimension, it's none because I don't know. I mean, it's just open how many image we need to apply. We don't care. But the dimension of the output, the shape of this feature map, it will be 32 times 32 times 32, as you can see it here, right? So it's a similarly. I mean, last time, but because we don't have the code, I mean, it would be nice, really, if we can, if I can put the code of AlexNet, for example, so you can just see how it looks like in the code. But we can do it. I can do it next time. So here we just defined 11 times 11. Sorry, I just defined 11 times 11. We didn't define the third dimension, because in reality the third dimension here will be the third dimension of. Why it's sorry. Okay. I mean, the third dimension here will be this one, right? We don't need to define it, because the input shape will be 227 times 227 times 3. So we don't need to define the third dimension of the filter, because it will get it automatically from the input shape, right? We just need to define those height and width, which is 11 times 11. We need to define the stride, which is equal 4, for example. We need to define if we will use padding equal same or void. When it's now here in this example, it's void because we didn't use 0 padding, right? Because the dimension shrinks from 227 to 55, right? Because we didn't use 0 padding. But this third dimension, 96, it will be number of filters. So if we need to define this, one, it should be conv 2D 96 filters, and the filter size will be 11 times 11, right? And the padding equal void, correct? It will be like this, and so on, right? So this is the input shape. Input shape equal 227, 227, 3. So it will be like this. So here we define the number of filters. This is the size of the filter. It's just in 2 dimensions. And don't worry about the third dimension, because it will get the third dimension from the input shape, right?
But then can I ask the question, and why is it then at the end it's the third dimension is increasing? So in Alex network, we start from 96, we start from 3, then we go from 296, then 256. Then I was thinking, well, actually, if it's something which is opposite of the PCA, for example, where we are trying to reduce the dimension. Here we just transport the data in a different shape.
Yes, I mean, we try to extract features, right? So this number, in fact, it's the number of features, correct? Wow. This number, it's the number of features. At the end, we will get a feature size or feature map, which has 6 times 6 times 256. So at the end, we will have 256 feature maps. Each has a size of 6 times 6. This is the most important, right? I don't care about those intermediate values, because those intermediate values, it will disappear. The most important for us is the output feature map. This is the output feature map. I will call it here output feature map, because we will send those output feature maps to my decision making, to the brain of my model. This is the brain, right? We will do, this is the feed forward part. This is the fully connected layer part. So this fully connected layer part, it will get those feature maps. So this part, it's like cooking. I mean, this feature extraction, it will try to cook, it will try to extract some features from this image, and it will try to cook it in several stages until we reach this one. This is the most important part here. We don't care about those intermediate values, because the most important part for me is that part. This is the most influential for us, because this is the part which will be used for decision making, for classification. So those intermediate values, we don't care, because it's hyperparameters. Someone will select those numbers, maybe someone else will select different numbers. Maybe they did that by an optimization algorithm to select the most suitable combinations. Maybe they do it by trial and error, right? But anyway, they did that, and finally we will get 256 feature maps, and each feature map has a size of 6 times. This is the most important for us, right? And as you can see here, we try to minimize the dimension 6 times 6. We use those max pooling or average pooling to reduce the size, height, and width. But at the end, we will get 256 of those feature maps. So this is the most important, because imagine that you are solving a problem and you will say, okay, I will extract four features. Someone else will say, no, I will solve my problem by 10 features. What do you expect? Which one will get better results? The one with 10 or the one with 4? If those feature maps are unique. So because in principal component analysis, you have, for example, 20 parameters, 20 column or features. So I will try to reduce it into 5. Someone else will say, no, I will reduce it into 10. I guess the one with 10, he will have more information about the problem, and we should expect that he will get maybe much better results than 5. Or it's a trade-off in reality, because I don't want to make it like this, because if you use them 5, maybe those 5 are enough, because those 5 carry 95% of the information or the data. But if you try to increase it, you will increase it until you reach 100% of the information. But the price will be the model complexity and the chances to overfit. So, but anyway, in this model, we don't care about those numbers in the middle. The most important for us is the output here, right? 6 times 6 times 256, right? This is the most important for us, because this is the high level feature maps. Those feature maps are low level, right? Because we are very close to the pixel values here in the first conv layer. And after that, we try to consolidate, try to apply more feature maps. It's like cooking process. We try to cook those features until we will reach something which can make sense for us. So this is the idea here. But the number of feature maps, it's a hyperparameter. You need to just select it. I mean, you need to select it, right? But the most important for us is the output feature maps, because this is the one which we will flatten, right? We will flatten and we will send to the first fully connected layer. This one, it's a fully connected layer. This is FEC1, and after that we will have FEC2, correct? And we have softmax layer for classification. It's binary classification, or it's 1000 classes, for example. So, but the most important, we will flatten here. This one, it's a flattened layer, by the way. This is flattened layer. And this flattened layer, it will just convert those feature maps 6 times 6 times 256 into one vector of size 9,1216, which is the multiplication of 6 by 6 by 256. So, from my point of view, maybe the most important is the height and width, because we try to get those high-level feature maps. So we need to try to reduce height and width as much as possible. But maybe this number 256, it's just he want to be sure that he will get enough feature maps, so he can solve the problem correctly. He can have, for example, high accuracy, for example. I hope if my explanation makes sense. Does it make sense?
Yes, but then at the end, we actually have 2 fully connected layers, right?
Yes, you have 2 fully connected layers.
Yeah.
In fact, it's 3, right?
Yeah, with the soft layer, yeah.
Soft layer. So it's 3 fully connected layers. This one, it's soft layer, as you can know the story, because we need to calculate probabilities. So we have 1 hidden layer, first hidden layer, maybe second hidden layer, and fully connected layer or output layer. This layer, it's a flattened, it doesn't have any parameters. It will just convert those high level feature maps or abstract level into 1D vector. So we can transfer those values to the first hidden layer and so on.
Yes.
Yeah, any other question? Any other question? Do you want to take a break?
Yeah, we can have 10 minutes maybe.
Okay, this is very good. Okay, we will stop here and we will take 10 minutes break. Thank you very much.